This week we're going to talk about magnetism. Magnetism is an interesting property that is in some respects difficult to understand, but in others it's fairly straightforward. First of all, there are naturally occurring materials in nature that have inherent magnetic properties, and these naturally occurring materials are called lodestones. And so there are actual rocks in nature that show magnetic properties. What you can see here is the person holding a lodestone that has a magnetic attraction to the metal wrench. Magnetite, which is black iron oxide, Fe3O4, is the material that makes up lodestones. So magnetite is a oxide of iron that is found in the natural rocks, and if there's a significant amount of this material in a rock, then it will demonstrate magnetic properties. Now, magnets are divided into two sections called poles. The poles are the ends of the lodestone where the magnetism or magnetic field's magnetic attraction is concentrated. There's always a north pole, which is the end of the pole that seeks the natural magnetic north in the earth. And then there's a south pole, which is the end of the magnet that is the opposite to the north pole and seeks the magnetic north pole. Now there's a law of magnets, just like there's a law of charges. And it's very similar in that like poles, south and north, attract each other. Unlike poles attract each other. Like poles repel each other. So here you see two north poles. They would repel each other. If that south pole swung around and came close to the north pole in the hand, then it would be attracted. This is the law of magnets, or law of magnetic poles. Produces what is known as a magnetic field. A magnetic field is the region around the magnet in which other objects are affected by the magnet. And just like when we showed an electrostatic field with lines of force or electrostatic lines, you can similarly show the magnetic field with magnetic lines. And notice that the arrows always point in such a way that the field lines go from north to south. And that is the direction that always occurs. The magnetic field lines always are shown as going from north to south. These lines are called lines of flux. They're imaginary lines. I mean, you can't actually see them. And they originate, or they indicate, the direction and strength of the magnetic field. The direction is shown with the arrow, and the strength is the concentration of the number of lines per particular area in question. Now, the magnetic force, very much like electrical force or gravitational force, follows what's called the law of magnetic force. And you see at the end is the formula for the law of magnetic force, which is a constant times the pole strength of one times the pole strength of the other divided by the distance square. And graphically you can see that this is a inverse exponential relationship in terms of the relationship between the distance and the magnetic force. So the force between two magnetic poles is directly related to the strengths of the poles and inversely related to the square of the distance between them. And notice that this equation is very similar to equations we've seen before, the gravitational force equation and the electrical force equation. And this is one of the phenomena in nature that some people think shows or is evidence for a divine creator, in the fact that these various relationships that are totally unrelated in terms of their physical presence, and yet their relationship mathematically is very similar. Now, when we look at what happens to these lines of force, it all depends on the media that these lines of force have to pass through and what happens. So there are various types of ways to describe this media, and one is the permeability. And there's a permeability of any particular medium that the lines of flux have to pass through. And air has a permeability, and iron has a permeability, etc. And what these diagrams show is the fact that ferromagnetic materials, that is, materials that encourage magnetic passage, they channel the lines of force in a particular direction. And other types of materials keep or prevent the magnetic lines from traveling through. Now, the higher the permeability of the substance, the more easily that substance can be magnetized. And iron is one of those substances that can be magnetized quite easily. Now, this top diagram on the top left, the purpose of this diagram is to show that you can use a material like iron to channel the lines of force in a particular way. And what it shows is that because the iron is more permeable than the air, that then iron passes or is channeled through that and away from the air. So you ended up shielding the area inside the iron ring because the lines go into the iron and do not travel into the shielded area. This is also shown with the iron bar, which can be magnetized at the same time. So magnetic shielding is when a permeable substance is used to trap lines of magnetic flux and to shield another area so that there is no magnetic flux or magnetic force going through a particular area. And so if anything inside these coils of iron would be shielded from any magnetic interaction. So a permeable substance can increase or decrease the magnetic force depending on how it's oriented. When you use a ring like this, it decreases the magnetic force inside the ring because the orientation is such that all of the lines of flux are trapped and moved away from the center of the circle. But you can also use a bar like in the lower left figure 1914 here and actually direct the lines of force in a particular direction. Now, magnetic fields are also produced on a molecular level, and then this is actually the genesis of magnetic force. On a molecular level, magnetic force is generated in three ways. And one way is the motion, and we'll go through this again in just a second, but it has to do with the motion of the electrons around the nucleus, the motion of the nucleus itself, and then the spin of the electrons on their axis. All of these would tend to produce magnetic fields. So the electron spin is actually the most important of those causes that causes magnetism in magnetic materials. So the magnetic spin, or the spin of each of these electrons, produces a magnetic field, as well as the fact that the electrons are moving around the nucleus, and then the spin of the nucleus also produces a magnetic field. And this is shown here. You see that the spin in the one on the left here, the spin of the electron on the left is counterclockwise, and that causes the field to be generated with the north at the bottom and the south at the top. So the counterclockwise spin, and there's something called the right hand rule. If you pick up your right hand and your fingers are pointed in the direction of the spin, then your thumb points in the direction of the field. And you can see that your thumb, if you take your right hand and have your fingers moving in a counterclockwise direction, then your thumb is pointed up, and that is the direction of the south end, and the north is opposite of that. If you turn your hand over, if the spin is changed to clockwise, then the field is reversed, and the south pole is down, north pole is up. So a strong magnetic field is produced by the spin of the electrons on their axis, which is what this diagram shows. Now a weaker field effect is produced because the electrons move around the nucleus as well. And again, if the electrons were shown to move counterclockwise around the nucleus, then the orientation of the field would be up. If they're moving clockwise around the nucleus, then the orientation would be down. And then lastly, the spin of the nucleus produces a very weak magnetic effect. So you have these three ways in which the magnetism is actually generated, or the genesis of the magnetic field. Now every material has this, obviously it has atoms and it has electrons that are moving and spinning, and so all of these produce something called domains. Now a domain is a group of atoms that have lined up and have produced a magnetic field, and this is shown on the left, the usual situation in most materials. Most materials have loose and random magnetic domains, and that's why most materials that you just run into do not exhibit magnetic properties. But if you line up all the domains by whatever means magnetizing the material such that all the norths and all the souths are oriented in the same direction, then you produce a macroscopic, that's M-A-C-R-O, macroscopic magnetic effect. And so this domain theory is the fact that magnetic fields of a magnet are a sum of thousands of these very small magnetic domains which become lined up. Now in the situation on the left, because they're loose and random, they cancel each other out, and you see no gross magnetic effect. But on the right, when they line up like this, you see a gross magnetic effect with the north pole being on the left and the south pole being on the right. So a magnet is a substance that is formed because the domains are lined up in such a way that they can work together. Now various materials have different levels of magnetic properties. And these are separated into diamagnetic, paramagnetic, and ferromagnetic. And diamagnetic materials are substances that all of the electrons are paired, and so there are no magnetic interactions. They are neither attracted or repelled by magnets. It says here they're feebly repelled by magnets, which is true. And they cannot be magnetized, and the lines of force will avoid a paramagnetic material. Remember I showed you in the previous so they're essentially impermeable to magnetic lines of force. Paramagnetic is sort of in between. It's a substance that has one unpaired electron per atom and therefore has weak magnetic effects. It's attracted but feebly to a magnet. Lines of force will pass through the substance but also pass through air. So there's some degree of preference to pass through the paramagnetic material, but it's not a strong preference, and so some of the lines of force would pass outside the material. And then there's the strong material called ferromagnetic material. It has several unpaired electrons per atom and is strongly attracted to magnets. It also channels or attracts or crowds lines of force and can be used in magnetic shielding. Either diamagnetic material or ferromagnetic material can actually be used as as magnetic shielding.